So hello everyone, welcome back to this lecture series on the topics of numerical methods. I am Dr. Vikas Maurya, currently working as an assistant professor in the Department of Mathematics at SR University. So in the previous lecture, we completed interpolation and different kinds of interpolation techniques for different types of data sets. Okay. Now in this lecture, I am going to start the numerical integration. Okay, which is basically used to find the approximate integral of any function fx. Okay, so the first question is why this numerical integration is important. Okay, so let us start with a very basic concept. So we all know that if fx is a differentiable function whose derivative is this small fx, then we can simply integrate this function, okay, this function fx. Then we will get, if you integrate this function from the interval a to b, then you will get fb minus fa. Okay, or we can write f dash x equal to fx. Okay, so what is capital F here? So capital F is antiderivative of small fx. Okay, and this equation is called the fundamental theorem of calculus. Okay, or we can say that this result is called the fundamental theorem of calculus. So most of the integrals can be evaluated using this formula. Okay, so what it means? It means by using this fundamental theorem of calculus, you can easily integrate as well as differentiate any function in a simple manner. Okay, but there exist many applications or many integral fx which cannot be evaluated exactly, okay, using this fundamental theorem of calculus. For example, if I take I equal to integral from a to b e to the power minus x square dx, okay, if I take this function, so in this case we cannot find any fx such that f of x equal to e to the power x square. What it means? We are not able to find any capital F of x whose derivative is e to the power minus x square. Okay. Similarly, you can consider in other examples. Suppose if I take I equal to a to the b square root of sin x dx. Okay. So in this case, it is not easy to find any function fx whose derivative is square root of sin x. Okay. Hence, it is difficult to evaluate the integral of such type of function. Okay. So the question is, how can you integrate this function? Okay, because the exact formula is not known. So to solve such type of integral or such type of problems, we will go through the numerical method. Okay. So this is the concept of numerical integration. Okay. Now, to overcome this, numerical integration or numerical quadrature rule is used, okay, to find the integral of such type of function. Okay, so since we are here talking about the integration, so our purpose here is to find the integral of this function, okay, function fx from a to b. Okay, so what is the meaning of this integral? Suppose if I take a random function, okay, suppose if I take a random function like this, okay, and suppose this one is a, this one is b. Okay, so what is the meaning of this integration? This integration means the area of this function, okay, area under this curve from interval a to b. Okay, so this is the meaning of this integral I. Suppose this one is I, then area under the curve from A to B is the meaning of this integral. Okay, so if you are unable to integrate this function, so exactly, so we will use the numerical method. Okay, so how we will do this? So first we will divide this domain into the finite number of subintervals. Okay, so the domain is given A to B. Okay, so first we will divide this domain into the finite number of subintervals. And how we will do this? Okay, suppose let us take another color. So let us divide this interval. Okay, see here we have divided this domain into finite number of equal subintervals. Okay, so what we will have here? So if we divide it, then we will have the function value at discrete data set. Okay, so suppose this is your original. Okay, suppose this is your A, this is your B. Okay, so let us define this is A, so suppose this is your B. Okay, so what is A here? A is your first data points. Okay, it is denoted by x0. Okay, and B is xn. Okay, so this one is your x1, x2, x3, x4 dot xn. Okay, so what is this point? This point is x naught f of x0. This one is x1 f of x1. This one is x2 f of x2. Okay, similarly this point is x3 f of x3. Okay, similarly this one is xn f of xn. Okay, okay, so if you divide this domain into finite number of subinterval, then you will get some kind of discrete data set. Okay, so if we have such kind of data sets, then we have, okay, then we can use here numerical methods. Okay, so for different kind of data sets we have different kind of numerical methods. Okay, so your first numerical method is called trapezoidal rule. Okay, so in mathematics the trapezoidal rule is, okay, a kind of numerical method which is used to find the approximate value of a definite integral. Okay, which is defined by the integral a to b fx dx. Okay, so here our aim is here to find the integral of this function under the curve from a to b. Okay, so how the trapezoidal rule work? So come to the previous slide. Okay, so here if you are joining these points by the straight line, okay, so if I join this point by the straight line, okay, and again first we will join x0 and x1, then we will join x1 to x2, then we will join x2 to x3, then we will join x3 x4 x4 x5 dot x5 xn. Okay, so we will join each points by the straight line. So if you join these points by the straight line, then this method is called trapezoidal rule. Okay, why? Because if you join these points, then you will get first you will get this area. Okay, this is looks like a trapezoid. Okay, again if you join x1 and x2, then you will get this area. Okay, again a type of trapezoid. Similarly you will get this area, If you join x2 to x3, and if you join x3 x4, you will get this area. Similarly, if you join these 2 points, then you will get this area. Okay. So first, what we have done here, we have divided the interval into the finite number of subintervals. Okay. And the distance of each interval is here is given h. Okay. So dot dot dot, each interval having distance h. Okay. Now if you see, so each intervals form a trapezoid with x-axis. Okay. So this form trapezoids, this one is formed trapezoid. Okay. And suppose the area of this trapezoid is a1, and the area is this trapezoid is a2. Okay. So suppose this one is a3, this one is a4. Okay. Dot dot, this one is an. Okay. Now the total area under the curve in this case is approximated by the sum of trapezoid area. Okay. So first we will calculate this area. Okay. Then we will calculate this area, then this one, then this one, dot dot, this one. Okay. And if you have all these area a1, a2, a3, a4, dot dot, an, then if you add them, then you will get total area. Okay. So we can write a1 plus a2 plus a3 plus dot dot an equal to total area. Okay. Total area. And what is the total area here? Total area from a to b, f of x dx. Okay. So this is the algorithm of trapezoidal rule. Okay. So how to find the area of each trapezoid? So suppose if I take the first interval x0 to x1. Okay. So let us take, if I take first interval x0 to x1, that is for n equal to 1. Okay. For n equal to 1 means here if you take n equal to 1, then you will get x0 and x1. Okay. So only one interval we have. So if you have if you take x0 and x1, then what is a1 here? A1 means the area of the curve from x0 to x1. Okay. fx dx. Okay. Now how to calculate area of this trapezoid? You can see, if so if you see, this diagram is looks like so this diagram is looks like trapezoid. Okay. So suppose if you have trapezoid and this one is a, b, c and d. Okay. So what is the area of this trapezoid? It is equal to, so area equal to here 1 by 2 into sum of parallel side. Okay. So what will be the parallel side? Parallel side is AB and CD. Okay. So AB plus CD into the height. Okay. So what is the height here? Height is, suppose this one is E, so height is AE. Okay. So this is the area of this trapezoid. Okay. So what is the here? What is parallel side here? So parallel side is f of x0 and f of x1. Okay. So we can write this is 1 by 2. So parallel side will be here f of x0 and f of x1. So f of x0 plus f of x1. Okay. And what is height here? Height is this distance. Okay. So this is your h. So we can write h here. So this is the area of the first trapezoid. Okay. h by 2 into f x0 plus f of x1. Similarly, you can calculate the area of second trapezoid. Okay. So a2 is integral from x1 to x2 f of x dx, which is equal to h divided by 2 f of x1 plus f of x2. Okay, similarly if you calculate an, okay, an means the area from xn minus 1 to xn, okay, area of fx dx. Okay, so what we will have h by 2 f of xn minus 1 plus f of xn. Okay, so now we have the area of first trapezoid, second, third, dot nth trapezoid. Okay, so if we will add them, then we will get total area. Okay, so what will be the total area here? So total area will be, suppose this one is I, capital I, so it is equal to, total area means from A to B, f of x dx. Okay, it is approximately equal to, so area of first trapezoid means x0 to x1 fx dx plus x1 to x2 fx dx plus dot xn minus 1 to xn f of x dx. Okay, you can also write a1, this is your a1, okay, this is your a1, this is your a2, this is your an. Okay, so you can also write in terms of a1, a2, an. Okay, so if you add them, then you will get the total area. Okay, so total area will be approximately equal to h, okay, divided by 2 plus f of x0 plus f of xn. Okay, so this one is your first point, this one is your last point, plus 2 times all the points between x0 and xn. Okay, so means f of x1 plus f of x2 plus dot f of xn minus 1. Okay, so this formula is called composite trapezoidal rule. Okay, what is h here? Okay, what is h here? H is equal to, this is b minus a divided by n. Okay, so if we have n equal to 1, if we choose n equal to 1, then we have I equal to, okay, only one sub interval we have. Okay, so we can write I equal to a to b f of x dx approximately equal to, so since n equal to 1, so only one sub interval we have, so we can write h by 2 f of x0 plus f of x1. Okay, or we can write approximately h by 2, since x0 is your initial point. Okay, so this is equal to a, so f of a plus f of b. Okay, so this one is called simple trapezoidal rule. Okay, simple trapezoidal rule. Okay, or we can sometimes we say that this is called 2-point trapezoidal rule. Okay, now let's come to the example section. So the question is here is, using the trapezoidal rule, okay, estimate the value of integral from 0 to 5 log 1 plus x square dx. Okay, and how we have to integrate here? By dividing the interval into 5 equal subintervals. Okay, so here number of subinterval is given n. Okay, so n is given 5 here, so n means number of subinterval is given so here number of subinterval is given n is given 5. Okay, so if we have n, so we can calculate h. Okay, now if you compare this function to the original integral, okay, integral a comma b fx, so you will get a equal to 0, okay, b equal to 5, and fx equal to log 1 plus x square. Okay, so here number of subinterval is given 5, so we can calculate the step size. Okay, so h equal to b minus a divided by n. Okay, so what is b here? B is given 5, minus a is given 0, n is 5. Okay, so if you solve this, you will get 1. So step size is given 1. Okay, so now we have all the data. Okay, so if step size is given 1, so we can now calculate the discrete data set. Okay, so let us draw the table. Okay, so what is your x here, and this is your fx. So we have to compute the integral from 0 to 5 with step size 1. Okay, so initial point will be 0, given 0, so step size is given 1. So so first point is, initial point is 0, first one is 1, second one is 2, third one is 3, fourth one is 4, and fifth one is 5. Okay, so this is your x0 here, this is your x1, this is your x2, x3, x4, x5. Okay, so we have total 6 data points and total 5 number of subintervals. Okay, so this one is your first subinterval, this one is your second subinterval, this one is your third, this one is your fourth subinterval, this one is your fifth one. Okay, so total 5 number of subintervals we have. What is the function value here? Okay, since the function is given log 1 plus x square, so if you put the value of x in that function, you will get fx. Okay, so what is f0? So if f0 means log 1, so log 1 is given 0. Okay, if you put x equal to 1, then you will get log 1 plus means log 2. Okay, so log 2 value is, if you calculate, you can use calculator here, you will get 0.6931. Okay, and f2 is 0.6054, not 54, this is 94. f3 is 2.3026, f4 is 2.8332, and f5 is 3.2581. Okay, so now we have the data points and their function values. Okay, so we can write the composite trapezoidal rule formula here. So what is I here? I is given, we have to compute the integral from 0 to 5 fx dx. Okay, so we can write the composite trapezoidal rule here. So it is approximately equal to h divided by 2, since we have 6 data points. Okay, so up to x5 we have to write. So first we will write the function value at first data point, then the function value at last data point. So what would be the last data point? It is x5. Okay, so f of x5 plus 2 times all the data points lies between x0 to x5. So f of x1 plus f of x2 plus f of x3 plus f of x4. Okay, so in this case, this is your formula. So if you put all these values here, you will get approximately equal to, what is h here? H is given 1 divided by 2, f of x0 is given 0 plus f of x5 is given 3.2581 plus 2 times, what is f of x1? F of x1 is given 0.6931 plus 0.6094 plus 2.3026 plus 2.8332. Okay, So solve this, we will get approximately, so 1 by 2 is equal to 0.5, okay, and 0 plus 3.2581 is equal to 3.2581 plus 2 times, if you add all the these numbers, then you will get 6.4383, okay, and if you calculate this, you will get approximately equal to 8.0675, okay. So this is the integration of fx, okay, over the interval 0, 5. So this is the approximate value of the integral, okay. Now let us consider one more example. So the second example is using composite trapezoidal rule with n equal to 6, okay. So number of subintervals is given 6. Approximate the value of integral I equal to integral from 0 to 3 and your fx is given 1 divided by 1 plus x square dx, okay. So the question here is compute the approximate value of the integral, okay. So first we have to use the composite trapezoidal rule, okay, and then find the exact value of this integral, okay, and then calculate the absolute error between exact and approximate values, okay. So let us start, okay. Again, if you compare this with your original function, then you will have we have a equal to 0 and b equal to 3, and your fx will be given 1 divided by 1 plus x square, okay. And what is more given to us, the number of subinterval is given, okay. So n is given 6. So if we have n, so we can calculate the step size. What will be the step size here? It is b minus a divided by n. So b means 3 minus 0 divided by n is given 6. So your step size in this case, it is 1 by 2, or we can write 0.5. Means we have to go from 0 to 3 and the step size will be 0.5, okay. So first we will draw the table. So what will be the table here? So this is, so first we will write x, then we will write fx. So your first point is given 0 and step size is given 0.5, okay. So first point is 0, then 0.5, then 1, then 1.5, then 2, then 2.5, then 3. So up to 3 we have to go. Since we know our function fx is given 1 plus x square, okay. So we can calculate f0, f0.5, f1 up to f3, okay. So what is f0 here? f0 is given 1, f0 point is 0.5 is 0.8, f1 is 0.5, f1.5 is 0.3077, okay, and f2 is given 0.2, f2 point is 2.5 is 0.1379, f3 is 0.1, okay. So this is your x0 here, this is your x1, x2, x3, x4, x5 and x6, okay. So total 7 data points we have here in this case, okay. So now first we will write the composite trapezoidal rule. So your integral is I, we have to integrate the function fx from 0 to 3 and fx dx, okay. This is approximately equal to h divided by 2. First point, the function value at first point means f of x0 plus the function value at last point f of x6, okay, plus 2 times all the data points between x0 and x6, okay. So write down their function values, f of x1 plus f of x2 plus f of x3 plus f of x4 plus f of x5, okay, because x6 is here. Now put all these values, so you will get this approximately 0.5 divided by 2, that is f of x0 is given 1 plus f of x1 is 0.8 plus 2 times f of x1 is given 0.5 plus 0. F of x1 is 0.8, okay, so 0.5 plus 0.3077 plus 0.2 plus 0.1379, okay. So if you solve this, then you will get this is your 0.25 into 1 plus 3.8912 plus 0.1, okay, which is approximately equal to 1.2478, okay. So what will be the approximate integral? So this is if so the integral is 0 to 3, fx is given 1 plus x square is approximately dx is approximately equal to 1.2478, okay. This is your approximate solution, approximate integral or solution we can write, okay. Okay, so since we know that the integral, the exact integral of this function, okay, so if you calculate the exact integral of the function 1 plus x square dx, okay, then you will get this is basically your tan inverse x, okay, so tan inverse x, and if you put limit, so limit is 0 to 3, okay. So what will be the exact integral? Exact integral is this is tan inverse 3 minus tan inverse 0, okay. So if you calculate the tan inverse 3, then you will get this is approximately equal to 1.2490, okay. So you can say that this is your exact value, okay. So this is your exact integral, okay, right? This is your exact integral. So how to calculate the absolute error? Absolute error is equal to, it is defined in the modulus by taking the error between the exact and approximate value, okay. So this is your exact integral minus approximate integral, okay. So what is the value of exact integral? So exact integral value is given 1.2490, okay, minus approximate integral value is given 1.2478, okay. So this is 0.0012, okay, or we can write this is the absolute error is around 0.12%, okay. So if you see, then the result is more close to the exact result, okay. So your approximate integral value is very close to the exact integral value, okay. So this is all about the composite trapezoidal, okay. So if you had any doubt, so you can write your question in the comment box, and thank you everyone for watching this video. Thank you.